Hello class, welcome to today's lesson in which we're going to continue with the subtopic 2.1 that we were dealing with yesterday. I'm going to write it here, 2.1, which is special products and factoring or factorization. Okay, so this is the continuation of yesterday's lesson. Okay, the class before we looked at this concept of special products and we dealt with the square of a binomial, the cube of a binomial, and the product of conjugated binomials. I hope that by now all of those things are very clear and you have somewhat memorized the formulas. It's going to take you some time to memorize them, and the more you practice, the better you will get at those, clearly. Okay, now today we're going to look into this concept, the concept of factorization. And in order to enter this concept, first we need some context or some background or some primitive concepts. The first one of those is the following: the concept of the greatest common factor, okay, which is frequently abbreviated as GCF. Whenever you see GCF, basically that's the same as greatest common factor, at least in the context of mathematics. Now, another name for this same concept is this: greatest common divisor, or GCD. They are the same, exact same thing. This and this are the same thing. So basically, whenever we say the word factor, we are saying the word divisor, and vice versa. Okay, what is this concept? What is it? I'm not gonna really explain it in. I'm not gonna give a formal definition. I'm just gonna explain it to you with an example, right? Let's do that for this time. So, for example, let's calculate. We're gonna calculate the GCD, the greatest common divisor, which is also the greatest common factor of the numbers 24 and 36. Okay, I want to calculate the greatest common divisor of 24 and 36. So how does this work? I'm going to explain to you the long version, so to speak, and then I'm going to give you the shortcut, okay? Because I need you to understand what you're doing or what this concept is about. So the first thing we have to do is list all the divisors of each of these two numbers. We are working with 24 and 36. So I write 24 colon 36 colon, and I'm gonna list all the divisors of each of these numbers. 2 is a divisor of 24, 3 is a divisor of 24, 4, 6, 8, and 12, right? Make sure that this list of numbers, all of these numbers are divisors of 24. Oh, and by the way, also 24, quite clearly. All of these numbers divide 24. And let's do the same for 36. The number 2 divides 36, the number 3, the number 4, the number 6, the number 12, and the number 18. I hope that no number is missing. I believe this is on 36 clearly. Yeah, I think it's complete. Okay, so these are the full list of factors of each of these numbers. Perfect. So if I want to calculate the greatest common divisor, what do I do? All I need to do is look at those lists and basically ask myself, what factors do they share in common? Okay, that's the reason for this word common. For example, the number 2, they share it, right? So they have this divisor in common. What other divisor do they share? or do they have in common? The number 3, right? I'm going to make these symbols in order to match one to the other. The number 4 is shared by both. The number 6, the number 12. And that seems to be the whole thing, right? Do you agree? They share 5 different divisors in common. Okay, now, quite simply, what does the G stand for? Greatest. So which one is the greatest of the common divisors? It's going to be 12. You see? And that's it. I'm done. The greatest common divisor of 24 and 36 is going to be 12. And my exercise is complete. Look at this notation. In mathematics, it's often written in this way. I'm going to read all of this. The greatest common divisor of 24 and 36. This is how usually it's written, okay? Not always, but it's usual. So I want you to be aware of this. Okay, so my problem is completely solved. Now, that took a long time because you have to list all the factors, you have to match them to see which ones they have in common, etc. Is this is all of this necessary? No, there is a much shorter way to get the greatest common divisor or the greatest common factor of two numbers, which I'm gonna show you right now. Let's erase all of this. And the technique is this. I'm gonna make a line here because I don't want to erase this yet. So let's now work on this side. Okay, so what is this technique? The technique is the following. I want you to get the prime factorization. I already told you what this meant, prime factorization, of your numbers of interest, which is in this case 24 and 36. Okay, and if you forgot about what this means, it means, doing this whole thing with the table, dividing over 2. Can we divide 24 over 2? Yes, we get 12. Can we divide again over 2? Yes, we get 6. Can we divide over 2? No. We go to the next number, which is 3. Can we divide 6 over 3? Yes. We divide it and we get 2. And finally, can we divide... I'm sorry, yeah, no, I made a mistake there. Can we divide 6 over 2 again? Yes, yes, we can. And we get 3. Now, can we divide 3 over 2? Clearly not. Can we divide over 3? Yes, we do it. We get 1. We finish. And the product of all these numbers is your prime factorization of 24. So I'm going to write it down in here. 24 equals 2 times 2 times 2 times 3. Okay, do the same for 36 on your own. I'm not going to do it. And you're going to get the following. 2 times 2 times 3 times 3. Okay, so all of this and all of this are my prime factorizations of 24 and 36. Remember, why is it called prime factorization? Because each of these numbers in this product is a prime number. Perfect. So now what? Now that I'm done with that, what should I do? Next, you must write this product 2 times 2 times 2 times 3 and this product and 2 times 2 times 3 times 3 in a reduced version, in exponential form. What I mean by that is this. Look at, for example, the number 2. It repeats itself 3 times. So there is a shorter way to write all of this. 2 times 2 times 2 is nothing but 2 to the 3, right? And the 3 remains as it was. Now let's do the same here. 2 times 2, that's equal to 2 to the 2. And 3 times 3, that's equal to 3 to the 2. Okay, this is what you want. This is what you want to do next after the prime factorization. Okay, and finally, the end of the method is the following. I'm gonna do it in yellow. Okay, look, the next and final step is asking yourself. Look at these to prime factorizations. These are still prime factorizations, only that in reduced form, in exponential form, so to speak. And ask yourself, what factors do they share in common? They share the number 2 as a factor in common and the number 3. You see? Okay. And finally, what you're going to do to get the greatest common divisor of 24 and 36 will be taking taking the least exponent of a common factor. Again, ask yourself, do they share the number 2 as a common factor? Yes, because you see the number 2 here and the number 2 here. Which one has the least exponent? We have 2 to the 3 and 2 to the 2. So this one has the least exponent. Choose it and paste it right here. Let's do the same with the 3. Do they share the number 3 as a common factor? Yes, because I see the 3 here and I see the 3 here. Which one has the least exponent? Clearly this one, right? Because it's 3 to the 1. Choose it and paste it right here. Times 3. Paste it is not a good word, but you know what I mean. Okay, and I'm done. I'm done. The greatest common divisor of 24 and 36 is equal to 2 to the 2 times 3, which if you calculate, 2 to the 2 is 4 times 3 is going to be 12, which is what we knew before. You see? We got the same result. So this is the shorter version. Now, of course, I'm taking a lot of time to explain to you how this works. You can do this very quickly. And in fact, a lot of people can get the GCD of 2 numbers or more numbers in like with the mind. You know what I mean? Like without doing anything. Sometimes it's simple. Can you do that in your mind? Sure, go ahead, no problem. I have no problem with that. But when you have problems, resort to this method. Okay, let's do another one. Now we're going to calculate the GCD of 3 numbers. Let's erase all of this. Of 3 numbers. So, what numbers? Let's work with, let's work with calculating the GCD of 40, 60, and 100. So like I said, some of you already know that the GCD will be 20, right? It's very simple to observe that's going to be the greatest common divisor. It's going to be 20. Now, how can I get it by means of a method? Because in this case, it is simple. But for some other numbers, you may not see it quickly. So we do the same thing. I write 40, 60, 100. Get the prime factorizations of each of these numbers. You're going to stop the video and get them. And then you're going to compare with mine. This should be equal signs. Okay, so these are the prime factorizations. Now let's reduce them to their exponential forms. 2 times 2 times 2, 2 to the 3, times 5, 2 times 2, that's 2 to the 2, 3 on its own, 3, 5, 5. 2 times 2, that's 2 to the 2, and 5 times 5, that's 5 to the 2. Okay, so we're done. Well, I mean, almost. And now the rest of the process is getting or writing the GCD. The GCD of 40, 60, and 100 will be what number? Okay, look at this, look at this, look at this. Ask yourself, do they share the number 2 as a common factor? Yes, because the number 2, it's in all of these three factorizations. You see, it's here, and it's here. So yes, indeed, the number 2 is a common factor. Which one has the least exponent? This one, 2 to the 2, or this one, right? It's the same. It doesn't matter. So it doesn't matter which one you pick. 2 to the 2, choose it, and paste it here. 2 to the 2. Okay, now I see here the number 3. So I ask myself, is the number 3 a common factor among all three factorizations? Clearly not, because this one doesn't have the number 3. I mean, don't say that this one works, because this is an exponent, okay? Okay, so no, because the number 3 is not shared, because only the 60 has the number 3 as a factor. So we don't even consider this one. Now, is the number 5 shared by all of three factorizations? Yes, because I see the 5 here, I see the 5 here, and I see the 5 here. Which one has the least exponent? The number 5 to the 1, not this one, right? So I choose it and put it here as a factor. So I'm done. My GCD of these three numbers is equal to 2 to the 2 times 5. How much is 2 to the 2? It's 4 times 5. How much is 4 times 5? It's 20. And I'm done. Okay? The GCD of these three numbers, the greatest common divisor, will be 20, which is what I said at the beginning, right? Because it's very simple to see that. And I need to show you the simple case so that for the more complex cases, you can apply the method, right? Usually a teacher should not explain a concept with a difficult example. One should strive for explaining with simple examples so that you get it. And for more complex numbers, the whole thing works in the same way. So this is how you work. This is how you get the GCD of three numbers. Now, question, guys. Do you think this method will change if instead of constants, because you have to agree that I'm giving you constants here, I want you to get the GCD of a constant, another constant, another constant. The same in here, you got the GCD of one constant and another constant. Now, what if the question is this? Find the GCD of, for example, the following. The number 24x squared, y to the cube, that's my first number, all of this. And the other number will be 36x y to the 4. Do you think the process will change? The answer is no. Why? Because these are numbers, right? Just like before. The fact that you don't know what x and what y are, what specific numbers, does not change the process. So let's get this one. Let's find it out. Okay, what did we do before? I wrote 20. I wrote my number, okay, and I need to write the prime factorization for such number. And it's very simple, because all you have to do is basically take the prime factorization of the coefficient, which we already knew. The prime factorization of 24 will be 2 to the 2 times 3 to the 2. I forgot. It's 2 to the, no, it's 2 to the 3. I'm sorry. 2 to the 3 times 2. And the variables are gonna remain like they are, like so. You see? And the same for this one. 36, the prime factorization is 2 to the 2 times 3 to the 2 times x times y to the 4. That's it. This is the prime factorization. So basically, the idea is the same. Getting the prime factorization of the coefficients, and the variables stay the same. You see, I did not change the variables. Okay, so now we can get the greatest common divisor between these two numbers. Well, I'm going to write it in here. It's already written. Okay, so I ask myself the same questions. Is the number 2 a common factor in this and these factorizations? Yes, because I see it here. Okay, I made a mistake. I'm sorry. This was supposed to be 3. I think I said 3, but wrote 2. Okay. So let's go back. Is the number 2 a common factor? Yes, because I see it here and I see it here. Choose the one with the least exponent. Circle it, paste it. Is the number 3 a common factor between this and this? Yes. Which one has the least exponent? This one. Circle it, choose it, paste it. Is the number x a common factor between this factorization and this factorization? Yes, because I observe it here and here. Choose the one with the least exponent and paste it. So you see, I'm not changing the process. I'm doing the same thing, but now with variables. Choosing the one with the least exponent. Is y a common factor between this factorization and this factorization? Yes, because I observe it in both of them. I choose the one with the least exponent and I paste it. And I'm done. This is the prime factorization. I'm sorry, no. This is the greatest common divisor of these two numbers. And I can now go to the product of these numbers. 2 to the 2 times 3. That's going to be 12. X, Y to the cube. And I'm done. This is the greatest common divisor or greatest common factor of these two numbers. Or these two terms. They are terms, right? Okay. So that's how this works, guys. Now, why is this useful? Why do I want to know how to get the GCD, in other words, the GCF of two numbers? Because that helps me factorize. That helps me factorize, which is what we want to do a lot in this stage. Basically, this stage is about you learning how to factorize very well and very quickly. So what is factorization? Factorization is this. Factorization is the process of expressing a sum of terms. And when I say sum, I mean algebraic sum. Like you may have, for example, 3x plus 4x squared minus 6x to the cube. Okay, and this is classified as a sum, all of this, because it's an algebraic sum. I know that you see a subtraction here, but you may think of this as basically this. Look, am I right? Can you see? So I can convert something that may look like a subtraction into a sum. So that's why this is generalized, and we say that this is just an algebraic sum. Okay, so factorization is the process of expressing a sum of terms as a product. Okay? Converting a sum into a product. In other words, I'm going to try to show you a diagram to understand what factorization means. Some term plus another term plus another term, you are given this expression, some term plus another term. Or maybe I think it's better to do this: term plus term plus term. And if you want to factorize this, you have to find a way to convert this into the factorization of, into the product of two numbers. So number plus number plus number equals number times number. You see, we are converting a sum, because this is a sum clearly, into a product. This is a product. Going from here to here is what is known as the process of factorization, expressing a sum as a product of numbers, expressing a sum of numbers as the product of numbers. That's what factorization means. Okay, so that now that we know what that means, how do we do it? With the help, well, there are many techniques, okay? And the most basic technique is the following: using the GCD, one of the most simple techniques. That's the one we're going to use today. Using the GCD to help you factorize. Why? Because, for example, what if I gave you this sum, this number or this term, plus this other number or term? Okay, number plus number, or term plus term. And I tell you, please factorize this expression, all of this expression. Okay, what would you do? You're gonna try to get the greatest common divisor of these two numbers. Okay, have we found it? Yes, it's this one, 12x y to the cube. Okay, that's why I wrote this precise thing so that we don't have to do it again. Now that you get the GCD between these two numbers, I'm gonna write it down here again. Okay, let's suppose that we already found it again, and you're gonna use it to factorize. How? You're gonna put it at the beginning of the factorization, like so. Okay, this is my greatest common divisor or my greatest common factor. You're gonna open up parentheses, and now you're gonna fill in inside these parentheses some new terms, so that when you multiply this times this new term, you're gonna get this first term in here. Okay, I'm gonna repeat that. You need to put in here a new term such that when you multiply this times this, you get the first term in your original sum. Okay, first, what coefficient should I put? 12 times what coefficient gives me 24? It's gonna be 2, right? Because 12 times 2 is gonna give me 24. Now, what x should I put? I have x here, and I have x squared here. So that looks like I need to write an x, because x times x will give me x to the square. And what y should I put in here? We have y to the cube, and we have y to the cube here. So it seems as though if I put a y or any other with any other exponent, for example y to the 2, it's not going to work, because y to the cube times y to the square is going to be y to the 5, which is not this. So in fact, in this one, I don't even need the y, okay, because I already have the y to the cube, which is in here. Okay, so it's 2x. We already found one. What about the other? We have 12 times some coefficient gives me 36. What's going to be that coefficient? 3. X times what x gives me x? None, right? I don't need to write an x here because I already have x and x. Now, y to the cube times what type of y will give me y to the 4? Well, clearly that's going to be y, because y to the cube times y will give me y to the 4. And I'm done. I'm finished, because I have expressed a sum number plus number as a product. Okay, this is a product. Why? Because we have number times number. You see, number times number. All of this should be considered as a single number, and that's how this works, guys. You see, this is the process of factorization. Now, again, these things can be done very simply. Now, technically speaking, do you have to guess these two terms? Well, no. You can actually do a process in order to find them. The process is this. It's very simple. Look, I'm gonna do analysis. Suppose that we don't know them, and I wanna find them out. I want to find this number and this number. First, I'm going to label them. I'm going to call this number A and this number B. You know, I could have chosen any other names, but I'm going to choose A and B. So if I know that A has to be a term such that when I multiply it by this, I get the first term in the sum, then I'm gonna write precisely that. I need that 12x y to the cube times a be equal to this 24x to the square y to the cube. And basically, if I want to find a, because that's the whole purpose of this, now I can just divide both sides over this number, or basically isolate a. Look at what I'm doing. You see, a will be equal to this divided by this. And since you know by now how to perform division of monomials, you should be quick to know that 24 over 12 is going to be 2. X squared over x is going to be x. And y to the cube over y to the cube will be 1. And that's it. We have found a, which is 2x, and which is what we have, what we had in here in a moment ago, 2x. You see? That's how you do it, if you don't want to be guessing. But in most cases, you can do it without doing all of these things. Factorization is actually a very, when the factorizations are simple, you can do them in your mind. That's no problem. I'm not asking you to do this whole process. I'm just teaching you the whole process because I want you to understand what you're doing, okay? Now that you understand the process, you can speed it up and take shortcuts and etc. Okay? It's up to you. It doesn't matter as long as you give me the right answer. Okay, so that's it, guys. I'm gonna stop it right here. I don't want to give you more examples because I already took about half hour of video. I think that's enough. Let's go to the exercises, and if you have questions, you can ask me. Thank you, guys.